Welcome to class. Today, we're going to talk about power series solutions to ODEs, in particular about ordinary points. If we're going to talk about power series solutions at ordinary points, we should talk about ordinary points first. If I have any linear ODE, notice here I've written it in standard form, so long as all of my coefficient functions are sufficiently differentiable. Complex analysis fans will know that really this word should be analytic, but that goes a little too into the weeds, and I think it'd be detracting from the main point to talk about that here. So for now, we're just going to assume that if they're differentiable as many times as I need them to be at x naught. So when I write my ODE in standard form, every coefficient function is sufficiently differentiable at x naught. That's what makes x naught an ordinary point. The opposite of a point that is ordinary is a singular point. So if that's not the case, if any one of my coefficients aren't sufficiently differentiable there, then that point is actually a singular point for the ODE. And when I have ordinary points, I can actually write my fundamental set of solutions as power series centered at that ordinary point. Let's take a look at an example. Let's take a look at this ODE. You'll notice it's not in standard form, so that's the very first thing that we should fix. Right? Let's write this in standard form by dividing the coefficient on my highest order over. So I'm going to divide everything through by x minus 1, and I get y double prime minus x over x minus 1, y prime, plus 1 over x minus 1, y, equals 0. You should notice immediately that I've just introduced domain holes into the coefficients here. Notice this gives me that x cannot be 1. In other words, x is a singular point of this ODE. So it is not possible to find a power series set of fundamental solutions at x equals 1, at least not yet. Stay tuned for that one. One is a singular point. In other words, we don't yet have tools in our tool belt to find power series solutions centered at 1. However, we can do it at basically any other point because these functions are actually infinitely times differentiable, and they're always continuous outside of the point 1. So let's take an easy point, 0. So we want to find a power series solution centered at 0. That is, we expect our solution, y of x, to have the form, the sum from 0 to infinity of ck x minus 0 to the k power. Now, in the same fashion as our method of undetermined coefficients and variation of parameters and everything, if that's what we assume the solution looks like, it should satisfy this equation. So let's see what plugging it in gives us. In order to do that, I'm going to need to take derivatives. So when I take the derivative, because I'm at an ordinary point, I can move that differential operator inside the infinite sum. And I can just take the derivative term by term. There's a lot of analysis going on under the hood that's beyond the scope of this video. So for our intents and purposes, just take the derivative of the formula, I guess, on the inside here, right? I have ck x to the k power. I'm taking the derivative with respect to x. Power rule tells me to bring that power down, subtract 1 from the power, and I'm going to do it again so that y double prime of x should look like the sum from 0 to infinity, ck k times bring the power down again, x to the k minus 2. Quick note though, when I plug in 0, I get 0. So I've actually lost my 0th term in this sum. Similarly, I've lost the 0th and 1st term in this sum. So I'm going to change those starting points to reflect that. And now we'll throw it into the differential equation. Importantly, I want to plug it in to the original form because this equation is not exactly the same as this equation. Do you notice, as far as we can tell from this equation, 1 isn't necessarily a problem for the differential equation, it just is for finding a power series solution. So we should plug back into my original equation. In other words, I should have that x minus 1 times y double prime, which is that sum, ck, k minus 1, x to the k minus 2, minus x times the sum from 1 to infinity, ck, k, x to the k minus 1, plus y, which is the sum from 0 to infinity of ck, x to the k, should equal 0. And now we've got a lot of fancy algebra to do. All right, I went ahead and cleaned up where we were at, made us some more room. If you recall, we just plugged in the power series solution y into the differential equation. We know that should equal 0. We've got a lot of cleaning up to do. The first thing that I see personally is those coefficients look a little funky. And the way I simplify these is by literally distributing them. After all, these power series are just big polynomials, so they'll behave algebraically the same way. Here, when I distribute it to the x, notice that's just going to bump the degree of the power series up by 1. In other words, since x doesn't depend on k, it can come inside the power series, and I get the sum from 2 to infinity, ck, k, k minus 1, x to the 1 higher power. Then I distribute it to the negative 1, and I'll get minus the power series as originally written. I'd encourage you to pause the video here, see if you can figure out how to do this multiplication on your own. Otherwise, again, since I just have x, I just need to bump the degree of this term up by 1. Oh, that should be a k. All right, I'll worry about that equals 0 in a second. Or here, equals 0. There we go. All right. Now, it's really tempting to start canceling stuff, but these power series are out of phase with each other. Essentially, what I mean by that is I can combine multiple power series into a single power series, but A, they should both start counting from the same power of x, so that it makes sense to factor out like terms, right, and combine like terms. B, they should start from the same index, right? Notice that, first of all, I have different powers of x across my 4 different power series, and I have different starting points across my different powers of x. I like to tackle those powers of x first. Do you notice that in my first series, I start by plugging in 2, which means I have an x to the 1 power. When I plug in 2, I have an x to the 0 power. When I plug in 1, I have x to the 1 power. And when I plug in 0, I have x to the 0 power. But I want all of them to start with the same number. I'm going to shift them up so that they all start with x. Because shifting up is usually a little easier. I can just strip out terms. 0 equals. In the first term, I'm already good to go. In the second term, I've got to shift up by 1, so I'm just going to strip out the first term. When I plug in 2, I get c2 times 1 times 1, or 2c2. Need a little bit more room here. Third term doesn't change. Fourth term, I need to strip out 1 term, so that it starts from x to the 1. When I plug in 0, I get C0 times 1. And now I start counting from 1. And sure enough, my first term will start with x to the 1 power. Now I can bully these so that they all start at the same place. How do I do that? Well, I want to make sure that I have x to the power, right? Or x to the dummy variable, dummy index. If this was just n, we'll say, let's call these n. If I was able to represent that power with a single index, then, of course, I would start counting all of these terms from 1, because they all start at x to the 1. So I'm going to go through and re-index these now, and I'll catch y'all in a sec. Whew. And there we are. So now, here's the advantage of putting all of these power series in phase with each other. In every term, in every power series, I have the same power of x. So I can combine all of those like terms into a single power series. I'm going to clean up the board so I have a little more room to work with. And I'll catch y'all when I have that. Okay, so combining all of my like terms, notice I essentially just factored out x to the n from each piece, from each formula, and these are the coefficients they had across all 4 of my power series. These are the terms I ended up stripping out. And I know that this whole thing should equal 0. This is finally the algebraic equation we need in order to start determining some of these constants. The only way, though, for a polynomial to be equal to 0, regardless of the input, is if the polynomial was 0 itself. Remember, x is a variable, and it can take on multiple different values. So the only way to guarantee I get 0 is by setting every power of x's coefficient to 0. Let's look at the constant terms first. It tells me that C2, if I set this guy equal to 0, solve for C2, I get C0 over 2. Great. Now, I also know, regardless of which power of x I have, its coefficient should also equal 0. We also immediately get that Cn plus 1 times n plus 1 n minus Cn plus 2 times n plus 2 times n plus 1 minus Cn times n plus Cn should equal 0. And it's usually most helpful to isolate the coefficient that has the highest index. In this case, that's Cn plus 2. So I'm going to isolate that term. Here you have it. And while this doesn't explicitly tell us our coefficients, it does help us determine them. We call this a recurrence relation. A recurrence relation. Notice I can get Cn plus 2 if I have the previous 2 coefficients. Now we arrive at a little bit of a conundrum, because I don't know how to find C0 and C1 just yet, but if I had them, theoretically, here's C2, pretty straightforward. All of the others, I can use this recurrence relation. C3 depends on C2 and C1. C4 depends on C3 and C2, and so on. So really, I just need those 2 coefficients in order to write down the solution to this problem. But that should line up with your experience in this class so far. Remember, this is a second-order differential equation. So we would expect a 2-parameter family of solutions. What we've just seen is that y of x is equal to C0 plus C1x plus the power series starting from 2. This is the point at which I can now determine my coefficients of use my recurrence relation. But this time, my coefficient needs to be k. So think about k as n plus 2. That means n is k minus 2. So I get c k minus 1 times k minus 1 times k minus c k minus 2 times k minus 2 over k times k plus 1. whoops, over k minus 1 times k, x to the k. But this is an IVP, right? So I actually can find those coefficients. I know that when I plug in 0, everything but c naught dies, and I should get -2. So bam, there's c naught. And I know that when I plug in 0 to the derivative, well, the only term that's going to survive is c1, and I get -6. So there we go. So how do I write down the solution from here? Let's look at the first couple of terms. Well, actually, I know the first couple terms. It's c naught, which is -2, plus c1 is +6. I misread my initial condition there. Plus 6x plus. Now, I could go in and well, I could just leave that term there, but I actually want to look at the first couple of terms so that we can see how to use this recurrence relation. Notice I'm going to do a bit of scratch work up here. When k is 2, my formula for the recurrence relation tells me that c2 formula, it's just c naught over 2, but c naught was -2. So c2 must be -1 plus -1 x squared. Let's move on to k equals 3, because now we've got to use our recurrence relation. I don't have another formula here. It tells me that when k is 3, I get c subscript, well, c3 is c subscript 3 minus 1 times 3 minus 2 times 3 minus 1 minus c subscript 3 minus 2 times 3 minus 2 over 3 minus 1 times 3. Or in other words, it should be 2c2 minus c1 over 6. c2 is -1. So I get, -1 times 2 minus c1, which is 6 over 6. Or -8 over 6. That simplifies to -4 over 3. X cubed, and so on.